Stem and leaf plots and frequency histograms are all well, fine, and good. They give us all kinds of interesting information. But it still leaves us with, in a sense, a whole lot of baggage. Either baggage in the sense of, okay, here's a summary of our frequency histogram. Now I can kind of describe qualitatively what that looks like. But how can we be very precise? What information does that really convey that we can use later on? It gives me some kind of idea and feeling for what the results of a test provided, but I don't know necessarily how to use all that, and I certainly from the histogram can't go back and resurrect the data itself. Whereas when I look at the stem and leaf plot, okay, I've got all the data, or I can resurrect all the data, but that's a whole lot of pieces running around, and I still don't quite necessarily know what to do with it. I got some qualitative kinds of ideas from this, what the mode and the mean and the median might be. You know, the median, I could actually kind of count up all the 70 data points. All right, I got 70 of them, so the median's between the 35th and 36th. So this is an ordered list. I could count up 1 to 35, find the 36th, and bam, I've got the median value. Okay. Or, you know, what some people do is they actually represent these numbers with X's, and then you lose the data, but you still have this sort of picture of what's going on. That's called sometimes a dot plot of the data, but that's not necessarily useful to get into some numbers that I can use later on, such as these kinds of statistics that we see up in here. And that's where we're going to head next. Is to talk about summary measures. And let's be a little bit more now formal and precise about how we define these various things. The median, again, is the 50th percentile value. So it is the data point for which the probability that our value is less than that data point equals 50%, or you could say less than or equal. And again, there's a little bit of a style there. If you have odd number, well, that's easy to find that one. If it's an even number of data points, well, then you take the one just above and below and you average those two out. The mode is the most frequently occurring data value, and I don't typically find that to be a very useful kind of number because I'm oftentimes working with real numbers, and so we know from a continuous random variable perspective the odds that any one of those numbers actually occurs is 0, right? Because exactly 5.253 gets smeared out with all the other infinite number of real numbers that could be possible outcomes. So it's for the mode, in my view, and also from a continuous random variable view, it's more useful to talk about the most frequently occurring sets of numbers within a range. It may be a fairly narrow range, but still a range nonetheless. And then there's the sample mean, which is nothing more than a fancy name for the sample average, which we calculate by summing up all of our data points. Right, so let's be real clear here and go back. Xi is the ith data value in our data set. Right? And it doesn't have to necessarily be ordered or not. They would be if you're doing the median value, but we're going to sum all those up, and then we're just simply going to divide by the total number that we have. Some people call that uppercase n, lowercase n, doesn't matter. Right? All three of these are measures of central tendency. You'll note from the stem and leaf plot that the mean value was reported to be 1403.6 seconds, 1403.6 cycles until failure. It is common to report the mean to one more digit than what the data is. I find that to be a little goofy in this particular case because 1403.6 cycles to failure is not all that meaningful to me, so I might report this as 1404 for the sample mean or the average. This is given the symbol, by the way, as X bar. Sometimes the median is given the symbol X with a little U, very shallow U, circumflux, I think they call that. And then sometimes the mode is given a little caret top on the top. Sometimes it's a tilde. There's a lot of different kind of symbols there. We won't go too far down that path because every author is just maybe a little bit different sometimes in those. Right, and those are three different measures of central tendency. Now, which one is valuable depends upon what it is you're trying to do or represent in the data. One disadvantage about the mean is that it is heavily influenced by outliers. So if we had an outlier, for instance, here in this data set where it took 10,000 cycles to failure, all the rest of them being the same, that would significantly influence the mean. Well, that may not be all that representative and all that real. Having an outlier that was around 10,000 wouldn't hardly affect the median, though, at all. Hence why that can be sometimes a far more significant representation of the center of the data. And of course, when you talk about house values in a region or a neighborhood, the median is usually what's used. Oftentimes, salaries are the same kind of thing because every community has someone who is that person who somehow has the enormous amount of wealth, and so their salary might be extremely large and not representative of what's going on. And that's kind of the whole point, that the measures of central tendency are somehow supposed to be representative of the center part of the body of the distribution. Right? Now, when it comes to dispersion or spread, then we have, again, a variety of ways that we might look at what that dispersion is. The simple one is just to look at the max and the min values and subtract the two, and that gives us a range. And again, for some folks, that's a particularly useful type of measure of dispersion. Presumably, you're going to get rid of any outliers that you believe are not actually representative of the population from which you randomly drew the sample set. So they'll kick out maybe those, but you're obviously heavily influenced by any potential outliers that are there. So the range can be potentially useful. Where one instance where it might be is something like where you believe a uniform distribution would be appropriate to model things, and in that case, the range and the coming from the max and the min is crucial because that's really the only parameters you have for the uniform distribution. Right, so it is common, it's easy to report, easy to find, but for a lot of engineering applications, not all that particularly useful. Instead, most commonly we're going to use some combination of either the variance, the standard deviation, or the coefficient of variation. The symbols that we have here are usually S squared for the variance, S for the standard deviation, and that's why we use S squared over here. It really comes from the standard deviation. And then the coefficient of variation, I'm not aware has any commonly used symbol for the sample, right? And that's a key thing here, that this is the sample variance. It's the sample standard deviation, the sample coefficient of variation. There it's just the sample standard deviation divided by the sample mean, right? And when we were talking about the population, the theoretical values, well, that was sigma divided by mu. In terms of how to calculate these things, it's going to be similar to what we were looking at before. Let's do this for the sample variance. we're going to take each data value, subtract off the sample mean, and square that. So that's a squared deviation, and add all of those up across the n data points. Now, that's just a total sum, and sometimes called the sum of squares of the deviations. And we want to find an average one of those. You could divide by n. And sometimes when you do that, some people will put a little subscript of n down there. Or you could do this instead as the same sum from 1 to n, and divide by n minus 1. Now, if you have a real large data set, the difference between these two is marginal. Really doesn't matter at all which one that you use. Depending on what you want to do with these is going to probably influence which you want to use. And it is far more common to use the formula with n minus 1 in it. And the reason why is, as we'll show in a later module, this is going to be an unbiased estimator. We haven't defined what biased means, but take it on faith. I don't work for the government. It's somehow more useful to us later on for certain kinds of applications. And so I'll leave and drop off the subscript on this one because it is the far more common one, and there's your n minus 1. Now, from a computation standpoint, it's usually when you're processing data, especially if you're doing it in a spreadsheet and you actually want to not use the function that's there. I don't know why you wouldn't, but let's say that you didn't. You want to calculate this out by hand, right? Well, it's usually a lot easier to break this apart, just like we did in the case of the variance for a population, where we expanded this product out and then we started pulling everything out into individual pieces in the sum, right? And we can show that this will turn out to be the sum of the xi squared, that's just the only term in this particular summation, minus n times the square of x bar. Right, that's the numerator. That's all broken apart. And then you'll divide by n minus 1. This is what the algorithm that's actually used in most functions you see in a calculator or in a spreadsheet or what have you. Right? And so note that if we were to have divided by n here, these n's would have canceled out, right, over here on this side, and we would have just had the average squared value minus the square of the mean, which is very much what we were looking at before, almost like an expected value of x squared minus the square of the expected value. This can be a very useful kind of thing. And again, if n is large, the difference between these is almost insignificant. Okay, for us, in our particular example with the aluminum test coupon data, our standard deviation is equal to the square root of the sample variance, and that is equal in this case to 402.4. Again, it's common to report this to one more decimal place than the actual data that you have, although you might in this case round it up to 402. It's sort of rule of thumb in a lot of engineering work where we only keep 3 significant digits somewhat arbitrarily. Okay. So those are two of the basic aspects of summary measures: central tendency and dispersion. And then we get to other shapes and how to quantify other aspects of the shapes of the histograms. So let's go back to those that we presented previously. Now when thinking about these shapes, it's kind of important to think about what the discretization that you have is. And so if you're qualitatively going to describe this distribution, when you look at it at this resolution, which was the one from the rule of thumb, you might be tempted to say, hey, the mean is somewhere around in here, and this distribution is relatively symmetric, like a mirror. You could flop the image, a mirror image, from one side of the mirror line, which would be the typically the mean that you'd be looking at. Right, well, if you look at this distribution from this view, it doesn't look very symmetric at all. It looks like it's got a little bit more piled up over here and extended out in its tail. Hey, wow, that's really what we want to focus. It's not how much is piled up, but rather that, gee, we've got more sitting down in the tail on one side. Let's dig into that a little bit more, both from how we might quantify that, as well as also being a little bit more precise about describing that. Right? And so this notion of asymmetry of the histogram of the data that we've collected, and this is also true of population or probability distributions, is that we capture this with the measure called skewness. Right? And we're going to emphasize here what happens out in the tails, far away from the mean. So we're going to look at the deviations away from the mean, but we're going to cube them, which means we're going to retain a sign if it's positive or negative, right, on the large side or the low side, and then it gets this big gigantic cubing. And we'll even get more gigantic here in the moment. We're going to sum all those up, and we'll find then the average of those, and that's what we're going to call skewness. Now, trying to figure out how big is big or how small is small is another tricky part of this. So what we're going to do is to normalize that by the sample standard deviation, but this time calculated with n. I know that's kind of goofy, right? Because now you got to run around. Did I divide by n minus 1? Do I divide by n? Well, out of Excel, for instance, in the standard deviation function, all you have to do is recognize that I just need to get a ratio between n minus 1 and n to get back to this one. I don't have to recompute this one right here. And this will allow us to normalize this. In some texts, we'll call this G1. This is the coefficient of skewness. Okay, and we're still left with, well, how do I interpret what that number is? So let's go back to a distribution such as the normal distribution, which is symmetric about its mean. Right? And in that case, for the normal distribution, the skewness is 0. And that's a key thing here, that 0 indicates symmetry. Right? G1 that is less than 0 indicates negative skewness. And that means that it's a shape that's heavy with the negative values, that we have a lot of values that are less than the mean. Right? And so that means that in our distribution we'll have a fat tail off to the left. Here's the mean, or X bar, depending on whether it's a population or whether it's the sample, and it's sitting way over big fat heavy tail. It's not, oh gee, where is most of the probability piled up, which might be over here on the right. It's no, not in the body, it's out here in the tails that we're interested in, a fat tail sitting out there. So that would be negative skewness. Positive skewness would be, well, just the flip-flop of that, where now you've got a fat right tail. That's positive skewness. That's the case for the log normal distribution, and unfortunately the log normal distribution has a little bit too fat a tail, or too much probability shoved out here in the tail. And if your interest is in modeling out in the tail, as it so often is in, say, civil engineering, then that's not so good. It means we don't have as accurate a model, and that's why the log normal is oftentimes not used out there. Right? for those cases. And that's why we have other kinds of distributions, such as the Weibull and that sort of thing, to model extremes. So there's negative skewness, there's positive skewness, and numbers that are real close to zero indicate that we have something close to symmetric. And in this particular case, we have a skewness coefficient that is calculated out to be negative 0.025. Right? So the negative number is not too surprising, right? We did see some data points that were sort of shoved out in the tail to the left, but overall, there was relatively symmetry in certainly a number of this close to zero, right? 0 minus 0.0. That's indicating to us that we have a relatively symmetric distribution that has a little bit of negative skewness, but not a great deal. Okay. One last measure here to talk about in terms of a quantitative summary measure, and that's an idea of the peakedness of the distribution. And here we're just going to go straight to sort of graphs like we have here to illustrate. We'll go back to a normal distribution where we have a single peak. And it turns out that for this one, that the coefficient of kurtosis, right, which is going to be defined as now the sum of the deviations away from the mean to the fourth power. So remember I said that was gigantic, and that's going to be even more gigantic, easier for me to say. And we'll find the average ones of those, and then we'll normalize now by the standard deviation of the sample raised to the fourth power. Right, so there's a preservation, so to speak, of the moments. Right? And think of this as a moment arm. If I'm a data point here, the distance from the mean is like a moment arm. And so then we're going to raise it to the fourth. So it's the fourth moment with respect to the mean. Right? And for the normal distribution, the kurtosis turns out to theoretically be equal to 3. Now, when you look at numbers oftentimes coming out of things like Excel and some other formulas, they know this, and so they don't like a number of 2.5 or 3.5 or 2.9 or that. What do we do with that? They like to instead subtract off the number 3 so that they get sort of single peakedness would be 0. Just kind of like for symmetry, we had a coefficient of skewness was 0. They kind of like that. They don't like using 3 as the basis. So you always have to kind of keep that in mind when you're pulling out numbers coming from different software packages. Did they do any massaging or shifting around of that? Right, I'm going to stick with 3 here for a moment. Right, so for another kind of distribution where maybe we have 2 peaks. So the mean is still sitting right in here, but now we've got data centered in 2 different places, multi-peaks. Then that's when we get g-values that are further away from 3. Right? And they'll tend to be less than 3. And in our case, from our sample that it turns out to be 2.56 for the aluminum, which means that we had a little bit more than 1 peak. And that sort of was, we could kind of see that potentially in our data. If we go back and look at a frequency histogram, we do have 1 primary peak there, but it does kind of have a gap in here before when we hit maybe another peak. You could begin to make arguments, well, what about this one over here? Well, that's where, there's a little bit of, in this picture, you got the resolution issue at stake. And there's also the other bigger picture question of, well, if we only have 70 data points here, and boy, if I have 700, I'm going to fill this in a lot better, and then the peaks will start to show up. And that's a little bit of preview about some of where all this is headed, and that is that, if you'll let me slide this down, we'd like to know, okay, here's our sample mean. What kind of quantifiable confidence can I say that the true mean is close to this 1404 that I got from this one random sample? And, well, gee, I'd also be interested in the variance that I obtained from my random sample. Now, before we go on, note that another way to think about this n minus 1 is that we've already we've used the data once to get the sample mean, and now we're going to use the data again, n minus 1, to get the sample variance. We've lost a degree of freedom. That's a little bit of the sense of why we get this unbiased estimator when we do the n minus 1. We don't when we use the n. That concept is kind of interesting as we go down and say, well, now I'm going to use the data even one more time to calculate coefficient of skewness, and then even one more time to do kurtosis. And in a sense, every time we reuse the data, we've lost a degree of freedom, so to speak. It changes the statistics of this sample measure that we're looking at. And that means this idea of a confidence interval that we're going to be developing in Module 8, or 7-ish, somewhere around there, and we're trying to quantify this confidence of, well, the sample value, how close is it to the true value, is going to be influenced by how many times that we've used the data, and what things do we know about the population and what things do we not. That's going to be a kind of a crucial, bigger picture aspect of this, and it turns out to have large degrees of confidence, even about the variance requires much larger data sets than just for the mean, and it gets even larger, and you can kind of get a feeling for this. We're cubing things now. Ooh, wow. I mean, we're not just using this the third time around, we're cubing things when we do this. And so we even need more to have confidence about the skewness, and even more to get into the kurtosis. And right now, all I really care is that you have this idea that we can measure the peakedness, but this number that you end up with, unless it's real close to 3, which is the single peakedness associated with a normal distribution, it's hard to really put numbers on its significance to what this means. What does 2.56 mean? Yeah, that's not an easy thing to really describe. It gives you some kind of general vague sense, but not a lot of information is contained there. And you don't actually hear a lot of people talking about the kurtosis. They'll typically stop at skewness if they even get to skewness. And even then, they usually do that, only talk about that when they're thinking about probability models as opposed to just simply summarizing something about the data set.